unfold.
Okay, let's unpack this. We're stepping into a cosmic crime scene, roughly 13 billion years old, set during, well, the most mysterious epoch in universal history. This is the deep dive into the case of the impossible galaxies.
And it really is a forensic investigation. I mean, for decades, our picture of the universe's early days has been dominated by one primary suspect, the Standard Model of Cosmology, what we all call 𝐏𝐿AM.
Right. And the crime scene, so to speak, is this period right after the Big Bang. We're talking about a starting point around 380,000 years out, stretching for about 400 million years. This is the Dark Age. It's just a profound silence when the universe was basically a gigantic cold fog of neutral hydrogen. You couldn't see anything.
And then the lights came on, the ignition. The moment the first stars and the first galaxies lit up and started burning away that fog, we call that moment the cosmic dawn.
Now, the Standard Model, 𝐏𝐿AM, and that stands for dark energy, the lambda, and cold dark matter, the CDM, it gives us a very, very specific script for how this should have all played out. It paints this picture of gravity as a patient architect.
And that patience is absolutely the key word. The theory basically mandates that structures have to build up hierarchically. You start with these tiny clumps of cold, dark matter, which is most of the mass, and they slowly pull in gas, and then these small clumps merge over, vast stretches of time to build bigger things.
So like starting with pebbles and then very slowly building up to boulders.
Exactly. So the prediction was crystal clear. The very first galaxies we'd see from the cosmic dawn should be, for lack of a better word, cosmic toddlers.
Toddlers. So they should be small, messy, chaotic, really low mass.
And importantly, dust-free, because they haven't had time to create the heavy elements that make dust. They should look like they're struggling to get going.
And for years, that picture was, well, it was just the accepted truth. I mean, the universe at those distances, at a redshift greater than 7, was basically inaccessible.
Right. Our best tool, the Hubble Space Telescope, could only just peek over the edge of that era. And even when it found candidates, it was functionally blind to the one thing that mattered most for this story, their total mass.
But then the forensic tools changed completely. The floodlight arrived, that stunning golden segmented mirror of the James Webb Space Telescope.
And this is the crucial part. JWST was designed, in large part, to confirm the standard theory.
To find those little toddlers.
To find the toddlers and validate that slow, patient timeline of gravity that 𝐿AM predicted.
Okay, so here's where the investigation takes its first massive turn. Because when that early data started coming down, especially from the Sears survey, astronomers didn't find toddlers.
No. They found fully formed adults.
It was an immediate crisis. I mean, it shook the foundations of what we thought we knew.
We were seeing sources at redshifts of 7, 8, even 10 that were massive, incredibly bright, and this is key, very, very red. They looked like they had stellar masses that were comparable to, or even bigger than, our modern Milky Way.
And just to put that into perspective for you, the Milky Way took 13 billion years to build itself up.
These things, according to the first pass estimates, did the same amount of work in less than 600 million years.
The analogy that just stuck, because it's so perfect, was it was like walking into a kindergarten class and finding a 250-pound bodybuilder sitting there among the blocks.
And you just have to ask, how did you get so huge so fast? It defies the timeline.
It defied the gravitational timeline. It suggested the early universe wasn't patient at all, but some kind of hyper-efficient forge running on overdrive. The media, of course, immediately dubbed them the universe breakers.
And that, right there, defines our mission for this deep dive. We are going to treat this as a complete forensic investigation. We're going to interrogate the Standard Model, examine the hard evidence from that critical 2023 paper by 𝐏𝐿AM and his team, and we're going to scrutinize every single suspect to figure out if these universe breakers are real or if they're just masters of disguise.
So let's start right where the crisis began, with the technology. The reason this problem didn't exist before 2022 is because we literally couldn't see what the universe was hiding from us.
That's exactly right. The main barrier is something called cosmological redshift, or just ZLO. Because the universe is expanding, light from a distant object gets stretched out as it travels to us.
So blue light becomes red light.
And ultraviolet light, which is what you get from hot, young stars in the early universe, gets stretched all the way into the infrared part of the spectrum.
And this is exactly where Hubble just hit a wall. a physical, unmovable wall that created what we now realize was a massive blind spot for stellar mass.
Yeah, Hubble was built for visible light. Its instruments only went out to about 1.6 microns in the near infrared.
But it was brilliant at one thing, which was finding these distant galaxies in the first place.
Oh, absolutely. It did that by identifying the Lyman break. It's a sharp drop in brightness caused by all the neutral hydrogen in the universe absorbing light at a specific wavelength. If you saw that dropout signature, you knew the galaxy was far away. But like you said, knowing it's far away doesn't tell you how much it weighs.
Right. And let's really nail this down because it's so important. Where is the mass of a galaxy actually stored? We see these beautiful, bright spiral arms, but is that where the heft is?
Not at all. The real bulk, the true stellar mass, is all locked up in the older, lower mass stars, your K&M dwarfs. These are the dim, boring, long-lived stars that make up the vast majority of a galaxy's population. And they don't shine in the UV. They emit most of their light in the rest frame optical and near infrared.
So the light that actually traces the mass.
The light that traces the mass. And if you take that crucial light from a galaxy at redshift 10, where does it end up on our detectors?
It gets stretched.
All the way out to 4 to 10 microns, a wavelength range Hubble was physically incapable of seeing.
So Hubble could only see the tip of the iceberg, the bright young stars, and then astronomers had to basically guess the total mass. They had to infer it using models.
And as we found out, that inference was dangerously misleading.
So the NIRCam revolution with JWST wasn't just about seeing farther. It was about seeing the right kind of light to measure mass properly.
That's the game changer. NIRCam, the near-infrared camera, covers the range from 0.6 microns all the way out to 5.0 microns. And that extra reach, especially beyond 2 microns, let us finally see the rest frame optical light from these cosmic dawn galaxies directly.
We could see the light from those K&M dwarfs for the first time.
We could finally weigh the iceberg, not just guess from the tip.
And with this new window came a brand new diagnostic tool, one that is absolutely central to this whole case, the Balmer break.
Right. The Balmer break is another one of these spectral fingerprints. It's an absorption feature, and its strength tells you something really fundamental about a galaxy's history.
So why does a strong Balmer break immediately scream evolved or mature galaxy?
Because for that break to be really pronounced, the galaxy has to have already gone through its first, most furious burst of star formation. The really massive, short-lived stars, the O and B types, they produce a flood of UV light that tends to wash out the Balmer feature. They have to have already lived their short lives and died off.
So if they're gone, you're left with the quieter, older stars, and the Balmer break just snaps into focus.
Exactly. It's a signature of age, of settled history. It suggests a galaxy that has built up a lot of stellar material over time.
And this is the paradox. This is what launched the crisis. JWST's NIRCam started finding sources that show the Lyman break. So they were definitely at high redshift, and they were intensely bright and red in those longer wavelength filters.
We're talking specifically about the F277WA, F356W, and F444W filters.
And just to decode those, the F444W filter is looking at light at 4.44 microns. At a redshift of 8, that filter is seeing exactly the rest frame optical light from those mass-carrying stars.
Correct. So the Lab A team saw these objects that were basically invisible in the short filters, the Lyman dropout, but were just blazing bright in F444W.
And if you take that immense brightness, that huge amount of flux, and you assume it's all coming from stars,
then the only conclusion your model can possibly reach is that there must be hundreds of billions of stars to generate that much light.
the models immediately spit out a number. 10 solar masses. An impossible number.
Hubble was blind, JWST closed the blind spot, but the immediate result was a full-blown astrophysical emergency.
Okay, so now we have to get into the specific evidence that really lit the fuse on this whole crisis. The original incident report, if you will. That
Right.
2023 paper from Lab A and their team.
Right. This is what quantified the shock for the entire community. They pulled their data from the Sears survey.
And what's so staggering to me is the size of the sky they looked at. It was tiny, about 40 square arc minutes, which is, what, a tenth of the size of the full moon?
A tiny patch of sky. But within that patch, they found exactly what they were looking for. These double break galaxies.
The ones that had both fingerprints.
Both. The Lyman break, which fixed their distance as being very, very far away, and then that subsequent rise in brightness that looked, for all the world, like a massive Balmer break.
And they found a sample of 13 candidates, but 6 of them were just. They were so extreme, they became the poster children for the universe breakers.
Let's use the classic example. Candidate ID 38094. Its photometric redshift Put it at z equals 7.5.
So the universe is just about 650 million years old at that point. A baby.
A baby? And yet, its estimated stellar mass was around 10 solar masses, 100 billion suns.
Which, again, is almost double the stellar mass of our own Milky Way, a galaxy that had 13 billion years to get there. It's unimaginable.
It implied a rate of growth that just completely breaks the standard rules of gravity. These things didn't just grow fast, they seemed to grow almost instantly.
And the reason for that mass estimate all comes down to the shape of its light, right? The V shape of its spectral energy distribution, its SED.
Exactly. The SED is just a plot of the galaxy's brightness across all the different JWST filters.
So walk us through that V shape. How does that V lead directly to 100 billion solar masses?
Okay, so the left side of the V is the sharp drop. You see it in the short wavelength filters. That's the Lyman break. That tells you, okay, this thing is at high redshift. Check. Then, immediately after that drop, you see this steep, sustained rise in brightness as you move to longer wavelengths. F277W, F356W, F444W. That's the right side of the V.
And that rising slope was interpreted as the Balmer break.
Interpreted as a massive Balmer break. And here's the crucial step. The astronomers then used stellar population synthesis models. These are computer models trained on how galaxies look in our local modern universe to try and replicate that V-shape.
And what did the model say?
To reproduce that incredible brightness in the F444W Billia filter, the model demanded an enormous reservoir of old, low-mass stars. The models work on a mass-to-light ratio. If you see that much rest-frame optical light, the model says, well, you must have a gigantic number of those mass-carrying K&M dwarfs to produce it.
And boom, out pops 10 solar masses. It was a direct, mechanical output of the model's logic.
But the crisis got even deeper. It wasn't just about a few individual heavyweight galaxies. It hinted at a structural problem with the universe itself, the density problem.
This is where it gets really serious.
Yeah, this is the systemic shock. Astronomers don't just care about one galaxy. They care about the total amount of stellar mass in a given volume of space at a given time. We call that the stellar mass density. And if you took the mass of just those 6 most extreme Lebbe candidates and you kind of extrapolated that density across the entire early universe.
The numbers broke cosmology.
They completely broke it. Our best lambda CDM simulations, based on years of precision data, predict a stellar mass density at that time of maybe 105.5 solar masses per cubic megaparsec.
And what did the Lebbe observations imply?
They implied a density closer to 106 sevens or even 107 the sevens.
It's 100 times more massive stuff than our fundamental theory allows for that early in the universe's history.
It implies the early universe was top-heavy, that a much larger fraction of all the available matter had already been converted into huge, mature galaxies than was thought possible.
It suggested structure formation wasn't slow and steady. It was brutally fast and efficient, violating that fundamental timeline. Okay, so the observational evidence was a bombshell. The community's next step, naturally, was to see if this could even be possible under the absolute most generous theoretical limits. This brings us to the prosecution's case, presented by Mike Boylan-Kolchin, who devised what is basically the ultimate theoretical stress test for the entire lambda-EDM model.
Yeah, Boylan-Kolchin's paper was brilliant because it stripped away all the messy astrophysics-like star formation rates and feedback and focused only on the inviolable cosmic budget. The standard model doesn't just predict what exists, it sets hard limits on what can possibly exist.
Let's lay out those limits. What is the universe's absolute unbending budget?
Okay, there are 2 main components. First, you have the halo mass function. Cosmological simulations can tell you with incredible precision the maximum number of cold dark matter halos of a certain size that could have possibly formed by a certain time.
So that's the size of the container the galaxy lives in, the dark matter halo.
It's the maximum possible size of the container, yes. Second, there's a limit on the contents of that container, a cosmic baryon fraction, or 5𝐾𝐃.
And that's the universal ratio of normal matter, the stuff that makes stars and us, to all matter, including dark matter.
Exactly. And we've measured this ratio with incredible precision from the cosmic microwave background. It's about 0.157. It's a fixed cosmic budget. It doesn't change.
So if you know the biggest possible container size, and you know the fixed fraction of fuel inside, you know the absolute maximum amount of material available to build stars, you can't make more than that.
That is the hard physical ceiling. And now we introduce the one variable that astrophysics controls, the baryon conversion efficiency. We call it epsilon.
Epsilon, because we know that turning gas into stars is a really inefficient, messy process.
Incredibly inefficient. If a galaxy could turn 100% of its available gas into stars, epsilon would be 1.0. but that's physically impossible.
Why? What stops it?
Feedback. As soon as you form massive stars, they explode as supernovae. They have powerful stellar winds. The central black hole can fire off jets. All of this heats up and blows away the gas, preventing it from forming more stars.
So the stars themselves regulate their own birth.
They do. And so the actual stellar mass of a galaxy, nap star, is just a simple equation. M star, FB, FB 𝐏𝐿𝐴.
And in the modern universe, what's a typical value for that efficiency for epsilon?
It's surprisingly low. In most galaxies and in all of our trusted simulations, epsilon rarely gets above 0.2 or 20%. It's just fundamentally hard to turn more than a fifth of your gas into stars before you blow the rest away.
So Boylan-Kolchin took the 𝐏𝐿𝐴 masses and just did the math. He asked, for these galaxies to exist inside the biggest possible dark matter halos allowed by theory, what must their efficiency have been?
And the results were just devastating. It was a mathematically proven violation of physics as we know it.
Give us the numbers.
The candidate at redshift 9.1 required an efficiency, an epsilon, of about 0.99.
99%. It would have had to turn literally all of its available gas into stars.
With no waste. The candidate at ZEO 7.5 needed an efficiency of 0.84. These numbers are just. They're physically absurd. It would mean that feedback, the central process that governs galaxy formation, basically didn't exist in the early universe.
And here's the real impossibility threshold, right? What happens if the 𝐏𝐴 masses were even a little bit underestimated?
That's the true crisis. If the masses were any bigger, or if the dark matter halos they lived in weren't the absolute rarest, most massive ones theoretically possible, the required efficiency epsilon would go above 1.0.
Let's stop right there. Epsilon greater than 1. What does that actually mean?
It means the galaxy contains more stars than the total amount of normal matter that was available in its entire dark matter halo to begin with. It's not just unlikely, it's a direct violation of the conservation of mass. It is physically impossible under standard cosmology.
So the stress test presented this forced choice. It said, either the masses you measured are wrong, or the entire standard model of cosmology is wrong. There's no middle ground.
And that, right there, focused the entire investigation. The primary objective became verify the masses, because if the masses are right, everything else is wrong.
Okay, so the Boylan-Kolchin test basically proved the situation was impossible as presented. The community rightly figured the problem wasn't with the laws of gravity, but with our interpretation of the light.
Exactly. Something had to be deceiving us. So the investigation expanded to line up the suspects, all the astrophysical phenomena that could potentially mimic the light of a supermassive galaxy.
The central question became, how could a galaxy that isn't ridiculously massive look so incredibly red and bright that it fools our models into thinking it weighs 100 billion suns?
Right. Let's go through the lineup. Suspect number 1, cosmic dust. Let's call it the mask.
The idea here is simple enough. We know dust makes things look redder. It absorbs and scatters away blue light, letting the red light pass through.
So the theory was, maybe these aren't old, massive galaxies. Maybe they're young, intensely star-forming galaxies, starbursts, that are just choked with dust. The dust mask would make a young blue galaxy appear old and red, fooling the models.
But the evidence from JWST, that V shape, was very specific. Does dust produce that sharp a feature?
And that's why dust was pretty quickly ruled out as the mastermind. Dust-induced reddening is, it's a smooth process. It creates a gentle, continuous slope across the spectrum. It does not naturally create that sharp double break fingerprint, the abrupt drop for the Lyman break, followed by that steep rise that looks like a Balmer break.
And there was other evidence against it too, right?
Yeah, if there's that much dust, it should be glowing. The dust absorbs UV light and re-radiates it as heat in the far infrared. But when telescopes like AMA looked for that thermal glow from these candidates, they mostly came up empty.
So dust might be an accessory to the crime, but it's not the main culprit.
Correct. So we move on to suspect number 2, a top-heavy initial mass function, or the imposter.
This one challenges a really fundamental assumption we make in astronomy. When we calculate a galaxy's mass, we measure its light, and then we multiply by a mass-to-light ratio.
And that ratio is determined by something called the initial mass function, or IMF. The standard IMF, which is based on what we see in our own galaxy, dictates a very strict recipe. For every one really bright, massive star you form, which gives you most of the light, you also have to form thousands of dim, low-mass M dwarfs, which give you most of the mass.
The top-heavy hypothesis suggests that maybe in the very early universe, that recipe was different.
Exactly. The idea is that the pristine metal-poor gas back then might have favored forming only the huge, massive stars and suppressed the formation of all those little low-mass ones.
Okay, so how would that create this deception?
It's a brilliant disguise. A galaxy with a top-heavy IMF would be incredibly luminous because it's full of bright O-type stars, but it would be genuinely low in mass because it's missing that huge reservoir of invisible M dwarfs.
So if an astronomer sees all that light and uses the Standard Model, which assumes all those little stars have to be there.
They're hallucinating mass. You're adding in the weight of billions of stars that simply don't exist just because your model is based on the wrong recipe book.
If this were true, it would solve the problem instantly.
Oh, yeah. The masses would drop by a factor of 10, maybe even 100. Epsilon goes right back into the safe zone. It's a really strong theoretical possibility.
But how do you prove it?
That's the catch. It's really, really hard to prove. You'd have to measure the galaxy's dynamical mass, its mass, from the motion of its stars, and compare it to the mass from light. And for these tiny, distant objects, that's almost impossible. So it remained a strong suspect, but unconfirmed.
Which brings us to our final suspect. Suspect number 3, early dark energy or the conspirator.
This is the nuclear option. This is the one that says, no, the masses are real, so cosmology must be wrong.
So EDE proposes that the expansion rate of the universe was different back then.
Sort of. It suggests there was this extra energy field that gave gravity a little kick very early on, causing structures to grow much faster than in the Standard Model.
And how would that solve the Boylan-Kolchin violation?
It solves it by changing the cosmic budget itself. It directly increases the number of massive dark matter halos that could exist at high redshift. It makes the containers bigger and more common, so you can fit those 100 billion solar mass galaxies inside without needing that impossible greater than 100% efficiency. It just raises the ceiling.
But that's a huge step. You'd have to rewrite the fundamental physics of the universe.
Absolutely. And standard scientific practice, the principle of Occam's razor, says you have to exhaust every possible conventional explanation before you do that. And it turns out the universe had a much simpler and frankly much more clever astrophysical trick up its sleeve.
And this is where the whole narrative takes a sharp turn. This brings us to the discovery of the little red dots, the LRDs.
Yeah, as JWST kept observing, its deep field images started filling up with these really peculiar objects.
And they were just dots. They weren't fuzzy extended galaxies. They were just unresolved, intense, single points of red light.
And they were everywhere at high redshift. What was so striking was their morphology. They were incredibly compact, often with sizes smaller than 100 parsecs.
Just for context, the stellar disk of our Milky Way is 30,000 parsecs across, so these are tiny.
Tiny and common. And their light had that exact same crisis-causing fingerprint. Faint in the blue, but blazing bright and red in the rest frame optical, that V-shape was back with a vengeance.
And here is the critical breakthrough. The investigation zeroed in on the LRDs when people realized that many of the original impossible galaxies from the Lab A paper, when you looked closer, they weren't extended galaxies at all.
They looked exactly like these little red dots. They were point sources, not distributed populations of stars.
Which immediately triggered the new hypothesis, the one that cracked the whole case open.
What if that red light isn't the combined glow of billions of stars spread out over a galaxy? What if it's coming from one single, incredibly powerful, localized source?
An active galactic nucleus, an AGN.
A supermassive black hole at the center of a galaxy, actively feeding on gas. A cosmic power plant that can outshine all the stars in its host galaxy combined.
And if an AGN is producing most of the light, then the models that Lobe used, the ones that assume all light comes from stars, they're completely wrong.
They're totally invalid. It's the perfect analogy. You're mistaking a high-powered spotlight for a gigantic pile of embers.
If you think the light is from embers, you calculate that you need a mountain of them to produce that much glow.
But if it's really a spotlight, you just need one small, powerful engine. The models were calculating the mass of the embers when they should have been looking for the spotlight.
But for this to work, the AGN has to be a master of disguise. It has to perfectly mimic the spectral signature of an old, massive stellar population. How does it do that?
This led to what's called the black hole star model, or the dense gas cocoon model, which really came together around 2025. The key is the structure. You have a central supermassive black hole, maybe 1 million to 100 million solar masses, but it's embedded in this incredibly dense, thick, spherical shell of gas and dust. It's completely enshrouded.
A cocoon. So the light from the AGN itself can't get out directly?
The UV and optical light is totally absorbed by this cocoon. The cocoon then heats up and re-radiates all that energy away in the infrared. That explains why these things are so bright in JWST's long wavelength filters.
Okay, so that explains the brightness. But how does it fake the Balmer break, the signature of old stars?
This was the absolute genius of the deception. It's not stellar physics, it's gas physics. The Balmer break is fundamentally caused by hydrogen atoms absorbing photons. It turns out that the superdense gas in that cocoon produces a feature called bound-free absorption at the exact same energy, the exact same wavelength as the stellar Balmer break.
So the feature that the models were trained to see as old stars was actually being created by the physical properties of the dense gas surrounding the black hole.
It was a perfect mimic, a spectral doppelganger. And the investigation even found a smoking gun, an object nicknamed the Cliff.
The cliff.
Yeah, and it had a Balmer-like break that was twice as strong, twice as deep as any physically possible population of stars could ever produce.
So stars literally cannot make a break that deep. It had to be gas.
It was the proof. It showed that gas physics was dominating the signal, and the dense cocoon model was the only thing that could explain it.
And this model also explained another nagging mystery, which was why some of these things had the broad emission lines of an AGN, but very little X-ray emission.
Exactly. If they're powerful, feeding black holes, they should be blasting out X-rays. But the model showed that in these superdense cocoons, the photons get scattered by electrons. This scattering broadens the emission lines, making it look like an AGN, but the cocoon itself is so thick that it absorbs all the hard X-rays before they can escape.
So the cocoon creates the disguise, hides the evidence, and pumps out all the red light. The perfect crime.
Flawless. The mass models never stood a chance.
So, with the physics of the disguise finally understood, the final step was to unmask these suspects, to go back to the original Lab candidates and properly account for the light coming from the black hole.
Right, to subtract the spotlight's contribution and see how much light was actually coming from the embers, from the host galaxy stars.
And when they did that, what happened to the masses?
They plummeted. The residual light, the actual starlight, dropped by a factor of 100 in some cases. The before picture was a stellar mass of around 10 solar masses. The after picture, once you subtracted the AGN, was a much more plausible stellar mass of around 100 on 99 to maybe 1095 solar masses.
A billion suns, not 100 billion, which is a perfectly reasonable size for a galaxy at that time.
Perfectly reasonable. The verdict was in. The crisis in cosmology was a case of mistaken identity. The universe breakers were not impossibly massive galaxies. They were normal-sized early galaxies that just happened to host abnormally bright, heavily obscured black holes.
The bodybuilder in the kindergarten was just a kid holding a very, very bright flashlight.
And with that, lambda CDM is secure. The Boylan-Kolchin Stress Test was passed not because the laws of physics are wrong, but because the input data was wrong. The stellar mass density of the universe snaps right back into line with predictions.
It's worth quickly running through the case files on some of the most famous early candidates, just to see how they were specifically resolved.
For sure. Let's start with Sears 93316. This was the one that briefly held the record for the most distant galaxy at a supposed redshift of 16.4.
Just 250 million years after the Big Bang.
But spectroscopy revealed it was a classic case of mistaken identity. It's actually a low redshift galaxy at Z4.9. Its bright emission lines just happen to fall in the exact same filters as a high redshift dropout, completely fooling the photometric fitting code. Verdict: an interloper. A fake.
Okay, what about GN-Z11? That one was confirmed as being really far away at Z10.6.
It was, but detailed analysis showed its extreme brightness wasn't from stellar mass. It hosts a furiously accreting black hole and has this weird nitrogen-rich chemistry. So it's a composite of a starburst and an AGN verdict exonerated. It's a rare statistical outlier, but its existence doesn't break the model.
And the original Lab A6, the ones that started it all.
Reclassified. Spectroscopy confirmed they were at high redshift, but also found the telltale broad emission lines of AGNs. They are the little red dots. Verdict: the mass was AGN light.
Finally, Maisie's galaxy.
Maisie's galaxy is a great one. Confirmed at Z11.4. And it's a genuine early star-forming galaxy. It's small, its mass is around 1 billion solar masses, and it's exactly the kind of toddler galaxy we expected to find. Verdict: a valid, confirmed early galaxy, but definitely not a universe breaker.
So the stellar mass crisis is well and truly over. And it teaches us that the biggest challenge in early universe astronomy isn't always finding new physics, but just being able to accurately tell one source of light from another. But, and this is where things get really, really interesting for me, solving one profound mystery has immediately created a new one, a possibly even bigger one, the heavy seed era.
That's it, exactly. The galaxies are normal size, which saves cosmology, but the black holes inside them are way too big, and there are way too many of them way too early. This has kicked off a black hole revolution.
We have found this huge population of supermassive black holes, 1,000,000 to 100,000,000 times the mass of the Sun, just existing routinely when the universe was less than 1 billion years old. Why is it a problem? Why can't they just grow fast?
It's a time problem. It's a fundamental growth problem. The standard story, the light seed hypothesis, is that black holes start as the remnants of the very first stars, maybe 10 to 100 solar masses.
Okay, so they start small.
They start tiny, and to get from 100 solar masses to 10 million solar masses in just 500 million years, you have to feed it constantly, nonstop, at the absolute maximum possible rate.
And there's a physical speed limit to how fast a black hole can eat, right?
There is. It's called the Eddington limit. As gas falls in, it gets hot and shines. That light, the radiation pressure, physically pushes back on the incoming fuel, throttling the accretion. To make the numbers work, these light seeds would have to feed at that perfect maximum throttle rate for literally their entire existence.
Which seems incredibly unlikely. The early universe was a messy place. Mergers, explosions. The fuel supply would have been constantly interrupted.
Right, so the sheer abundance of these little red dots, all these powerful early AGNs, points strongly to a different idea. The heavy seed hypothesis. This is the idea that the universe didn't bother starting small. It jump-started its black hole population by forming them big right from the get-go.
How do you do that? How do you form a black hole that's already, say, 100,000 solar masses without going through a star first?
This is the theory of direct collapsed black holes, or DCBHs. It's an exotic process. You need a massive cloud of pristine original flavor gas from the Big Bang, and you need to make that entire cloud collapse into one single object without it breaking up into thousands of individual stars along the way.
What stops it from breaking up? That's what gas clouds normally do.
You have to prevent it from cooling down too quickly. The main coolant in pristine gas is molecular hydrogen, H2. If you can destroy the H2, the cloud can't cool efficiently, it stays hot, and it can collapse monolithically into one single massive object. A 105.55 solar mass black hole born in one event.
And what destroys the molecular hydrogen?
A strong bath of ultraviolet radiation from a nearby, vigorously star-forming galaxy. That UV light shreds the H2 molecules, setting the stage for direct collapse.
So they were born big, instantly solving that 500 million year growth problem. They didn't have to climb the ladder. They started near the top.
Exactly. And this isn't just a theory anymore. We're getting observational hints. Analysis of an object nicknamed the Infinity Galaxy showed features consistent with a black hole forming directly out of a huge column of shocked gas during a merger.
A direct gas-to-black hole transition.
It suggests the mechanism is real and it happens in the early universe.
So this whole journey, this whole JWST saga, which started as a crisis about how galaxies grow, have completely pivoted. It's now a revolution in how black holes are born.
The cosmic dawn wasn't just about stars. It was the era of black hole seed generation.
This has been one of the most exciting forensic journeys in modern science. We started with a crisis that genuinely threatened to rewrite the entire history of the universe, these impossible 100 billion solar mass galaxies.
And we ended up with this really elegant, profound resolution. It was all driven by one single exotic physical effect. These super dense gas cocoons around powerful hidden black holes, which were perfect mimics of old stars.
The ultimate takeaway for me is that the entire focus of early universe studies has shifted. The cosmic dawn wasn't this slow, patient, gentle process we imagined.
No, it was a black hole era. It was characterized by the rapid, violent birth of these giant seeds, a process far more efficient and dramatic than we ever thought.
So the universe didn't break its own laws. It just hid its most exotic creations, these black hole stars, in plain sight, waiting for an instrument like JWST with the infrared vision to finally unmask them.
The Standard Model is safe, but our picture of that first billion years is now much, much wilder.
So here's the final provocative thought we want to leave you with to mull over. If the existence of these heavy seeds, these direct collapse black holes, is now the new observational reality, it means that the conditions in the Dark Ages had to be just right to make them, and to make a lot of them.
So what fundamental things are we still missing about that environment? about the nature of those first pristine gas clouds, about the strength and ubiquity of that UV radiation bath that was needed to trigger their collapse. That is the brand new puzzle that JWST has handed us.